Previously, we talked about the relationship that n choose k has as we vary k. We noticed that there's a symmetry that occurs based on whether you pick a subset of size k versus the subset of size n minus k. And we notice that there's actually a symmetry that occurs. This actually makes it easier to compute n choose k if we were trying to determine all the values of k. In addition, we also figured out a reasonable definition for when n is strictly less than k, what exactly n choose k would be. In that case, we noticed it was a 0, right? That's also a convenient thing for us to have. This brings me to now talking about something called Pascal's triangle. A neat mathematical structure. You can constructively build it to any size you like, but it's going to provide us a valuable relationship provides a valuable relationship in combinatorics. So you're going to find that this structure that we're going to talk about every once in a while just decides to spring up, and things that we discuss in one context may actually pop up within the context of this Pascal's triangle. So it's something that is worth knowing about. And it connects all sorts of different things, like number sequences, different properties that you may study in one context may actually appear in this structure called Pascal's triangle, which we're going to derive what that is here shortly. But namely, the way we're going to explore this topic is we're going to see and extend our ideas we talked about before. You know how we varied k in our computation of n choose k? Let's vary n. Let's increase values of n successively and see what happens. So all sorts of things pop up in this so-called Pascal's triangle. So I'm not going to focus so much on that right now. Instead, I want us to go through the exercise of computing n choose k, and let's see if we could see anything interesting that's happening. So I'm going to vary n vertically. I'm going to have 0, 1, 2, 3, 4, 5. And we're gonna just allow it to keep going. And I'm going to have k, which is going to be 0, 1, 2, 3, 4, and 5. And I'm going to allow this to keep going. So what we're going to do is we're going to build this table . I'm going to write a little bit smaller, but fortunately for us, that shouldn't be too much of an issue. Okay. So first, let's figure out what 0 choose 0 is. Well, if it makes it a little easier to study what 0 choose 0 would be, what would it be if I have... So I have no elements, and I'm choosing none of them. But the thing is, there is a set with 0 elements. It's the empty set, right? If I choose none of them, what is that? Well, I'll let you think about it, but the point is there's only one of them. But notice now after this, then k is going to be greater than n, meaning that I'm trying to pick subsets that are bigger than the set itself, meaning it has more elements than the set itself. So all of these will have 0 in them, and so on. It'll just keep going with zeros after this. Likewise, because of this property as well, I can already tell you which ones are going to have zeros in them right away. So notice that 2 is greater than 1. 3 is greater than 2. See, 4 is greater than 3. And 5 is greater than 4. So you know all those are going to have zeros. In fact, this will continue going on forever in these rows of zeros. Next, let's talk about, so instead of going row by row, I'm going to go column by column at first and see if you can see any easy ways, at least for the first 2 rows, I'm going to do this. So I'm going to have 1 choose 0, then I'll have 2 choose 0, 3 choose 0. So I'll do the first column because it's so dang easy. 4 choose 0, then I'll have 5 choose 0. So what should all of these be? Well, based on the same argument I gave you, okay, I choose none of them. But there's only one subset that has no elements in it, right? It's the empty set. It's only one of them. So all of these will be 1, right? So all of those are 1s. Naturally, you can use our property we just talked about to figure out what this would be. What's 1 choose 1? Well, I have 1 element. I want all the subsets of size 1. How many of them are there? Just 1, right? This is just n choose n. That's just 1. And you can do the same thing, right, for all of these. As soon as you get where you're actually just along the diagonal here, whenever you would have a, like 2 meets 2, that's just 2 choose 2, right? Right? 3 choose 3, it's just 1. You do the same thing here. 4 choose 4, that's just 1. We have 5 choose 5, that's just 1. Now, notice, let's try to use the property we just talked about previously about how there's a symmetry that happens over the values of k. So whatever goes right about here in this row, this will be kind of like the mirror point. So there's 1 on this side, 1 on that side. Whatever's here is going to be where it differs, possibly. Likewise, in this row, it will be that everything will mirror like this. And likewise, something will similar happen over here where it will mirror like this. So we actually don't have to compute all of the values very delicately. We could just take advantage of the property we just proved previously. So what's going to go right there? Well, that will be 2 choose 1, right? Well, what's 2 choose 1? That's just 2, right? If you're not sure about that, just pull out the definition for 2 choose 1. So I have 2 elements. I choose 1. So I have 2 elements. So for example, if the set had A and B in it, the subsets would be A and B. So those are my 2 subsets. And I can do the same thing actually in this entire row, sorry, this entire column, right? You can see that it's just me picking 1 off from each of the elements and putting its own subset, right? So 3 choose 1 would just be 3. 4 choose 1 would just be 4, right? 5 choose 1, that's just 5. Yeah, that's quite the abomination of a 5, okay? Just roll with it. Just roll with it. It's sort of melting there. It's like that look when you have something in the microwave a little too long. That's what happens. So now armed with the material that you do know, what can we fill in here? Well, we'll notice that there's this one here. Well, that's 3 choose 2. Well, what's 3 choose 3 minus 2? That's 3 choose 1, right? So that is just, so 3 choose 2. So remember, we know that, so just remember that we know that n choose k is equal to n choose n minus k, right? So that means that if I give you something like 3 choose 2, then that's the same as me saying 3 choose 3 minus 2, which is just 3 choose 1, right? We already computed that. So this is just 3 right here. As I suggested, we have sort of like this mirror point. Likewise, we can do the same thing over here, right? So so I got 4 choose 1 So I have 4 choose 4 minus 1 is 4 choose 3, right? So 4 choose 3 is going to be equal to 4, right? And you do the same thing here as well, right? You have 5 choose 4. Well, that's just 5, right? Now, let's figure out what's going on in here. Okay, 4 choose 2. Now this one, unfortunately, we can't just simply attack in this direct way, but we haven't really observed kind of the killer property of the configuration that we have set up here so far quite yet. If you've noticed anything interesting going on with this table, you might be able to guess quite quickly what's supposed to go right there, but I'm not going there quite yet. Remember, we're still getting ourselves familiar with this binomial coefficient. So let's try to compute out what 4 choose 2 is. 4 factorial over 2 factorial 4 minus 2 factorial, right? We actually computed this in a previous exercise, right? Because it's just 4 times 3 factorial. But I can extend it even further. I'll go 4 times 3 times 2 factorial over 2 factorial, 2 factorial. So the 2 factorial, they go. Then I have 2 factorial that turns this into a 2 because 4 divided by 2 is just 2. So I have 3 times 2, which is just 6, right? 6. Interesting. Interesting. Now, let's figure out what this one is. If we could figure out what this one is, then we know the answer for this one based on that property right there. Remember, it just mirrors like this. So, let's figure out what 5 choose 2 is. 5 choose 2. 5 choose 2. Well, it's 5 factorial over 5 sorry, not 5 factorial, it's 2 factorial. 2 factorial, 5 minus 2 factorial. So it's 5 factorial, 3 factorial. So I'm going to have 5 times 4 times 3 factorial over 2 factorial times 3 factorial. The 3 factorials, they go away. 5 times 4 divided by 2, it becomes 5 times 2, which is just 10. So this just ends up being a 10. And by our reasoning that we gave previously, 5 choose 2 is equal to 5 choose 3 because it would just be 5 choose 5 minus 2, which is equal to 3 in that case. Because 5 minus 2 would be 3 here. So it's 5 choose 3. I uttered that a little bit strange at first, but it's 10. It's 10. Now. What I want to do is try to figure out a general pattern that's going on with this setup. So the first thing I need to acknowledge for you is what Pascal's triangle is. So let me just use a different color here. So this diagonal here and below, this, what I've just described here, and below, this is what Pascal's triangle is. It goes on indefinitely, downwards and to the right. But there's something interesting going on with this triangle. So I must stress that this is Pascal's triangle aligned to the left. Some people will just write Pascal's triangle like a like sort of a triangle, literally. So something like this. So sort of like this. So it'll be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, like this. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. And it keeps going on forever downwards to sufficient size that you would like. So sometimes people will just write Pascal's triangle out like that. There's lots of neat things about Pascal's triangle, but I want us to notice something that's really neat about this triangle. So I really want you to think carefully about this. Okay. Why would it be that the answer here is 2? Well, it's when I have n is 2 and I have k is 1, right? But do you notice anything? Now keep in mind, we haven't really answered why this would be the case. But do you notice something just peculiar about this? Do you notice that 1 is here, 1 is there, and that's a 2 there. And notice that 3, and there's a 3, and there's a 6 right here, right? Do you notice also that 6 and a 4 is right here, and then that's a 10 right there? You also notice that 4, even 4 and 6, that's 10. We got 4 and 1, that's a 5. Heck, even it works on our edge cases too. Like with 1 and a 0, there's a 1 right there. It even works in these edge cases, but most certainly we just care about when it's simply just a positive integer and another positive integer. So notice, for example, even in this edge case here, like 1, 0, 1, 1, 2, and 3, 1, 3, 4. Notice that it's really something interesting going on here, right? Do you see that all I have to do to compute any one of the cells that belongs to a positive integer? So you notice that if I go, say k is 1 or greater, or n is greater or equal to 1, I can compute any one of the cells that exists over here, because all of these are just 1, right? And it's just 1 and then a whole bunch of zeros, right? I can compute each one of these successive ones, and this isn't the right color. I need a red, and I'm losing markers. I'm losing markers, everybody. So please notice that I can, if I add the results in the immediate up to the left and the one directly above it, it equals whatever is in that spot. So notice that 3 is equal to 2 plus 1, right? Interesting, right? You do the same thing here. So it's 4 plus 1 is equal to 5. Interesting. Well, let's extend out our triangle now to try to figure out what's being written down here. What would go right here? This is n choose 0, right? That's n choose 0. This would be n choose 1. This would be n choose 2. This is n choose 3. N choose 4. N choose 5. And then I have n choose k minus 1. And I have n choose k right here, right? What would go in the n plus 1 row? This would be n plus 1, choose 0, n plus 1, choose 1, n plus 1, choose 2, n plus 1, choose 3, n plus 1, choose 4. Then we have n plus 1, choose 5. And keep in mind we still have our dot, 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 right? This keeps going. And keep in mind, all of these will still have 0 in them. All of these are just zeros up above here. All of this is zeros. These are all just zeros, dot, dot, dot. Don't want to make them look like ones too much. All these are zeros. That's the point. Then, what if I cared about this particular cell? This one right here. What about this one right here? Well, this is K, column K, row n plus 1. If the relationship that we've noticed here in our, and keep in mind, we don't know this is a matter of fact yet, right? This is just a speculation that we have. We haven't proven this. But if I take our idea from here, what would this mean in terms of the notation that we've been using? Well, it says that if I add the cell's value directly above me and the cell up and to the left directly, I should get what's right here. That's what it says. Okay, so what should go right here then? Well, let's think about that. Well, either way, whatever is here, we know that cell, this cell will be, will be n plus 1 choose k, right? That's what this will have in it. So I want you now to think about what should go right as an equivalency right here. And this will give us what we call Pascal's formula. So you wonder what Pascal's triangle is? This is what Pascal's triangle is. It extends on forever like this, and it keeps going. But it's named after the mathematician Blaise Pascal. Did all sorts of interesting stuff in his life. A lot of neat mathematical concepts, including even calculators. So some early computational history can be associated with Blaise Pascal. So now let's put this all together. So if ever you want to compute successive entries in Pascal's triangle, we can use what we're going to come up with next here, Pascal's formula. Consider any n and k that are positive integers, where k is less than or equal to n. Here's what Pascal's formula is. It's that n plus 1 choose k. Remember, that's the cell that we're interested in on our table over there, some arbitrary row and column. This will tell us, based on our intuition, you mind we still have to actually prove it, is that this is n choose k minus 1 plus n choose k. Remember, this is the one that is directly above, so this is the cell directly above the one that we're interested in, and this is the one that's up and to the left. So once you have that in place, you can compute successive cells of the table. So we're going to use a combinatorial argument to prove this, and it's going to be surprisingly simple. Because something that looks kind of daunting like this, it'll match quite interestingly in a combinatorial view of things. So you got to think about it in terms of sets and subsets. And what we're going to do is we're going to take advantage of the addition principle to do this. That actually, when we talk about our subsets, there's actually a special property that's going to exist from one row to the previous, like the one directly above it. There's going to be a very special relationship that exists there that we're going to exploit. So consider an arbitrary, so I'll say consider any set A with n plus 1 elements. And I'm just going to give those elements a name, where A is equal to A1, A2, all the way up to AN plus 1. Now, here's the killer observation. This is going to come back to our basic counting principles, is observe the following. Observe that any subset of A of size k either contains a n plus 1 or not. Those are only two possibilities if I fix one of the elements. In this case, I'm going to use the last one. So it's either going to contain a n plus 1 or it isn't. Right? Because so those are the only two possibilities, right? So if I pick a subset of size k, remember, we're going to be considering the size of n plus of a subset of size k for a set with n plus 1 elements. There's only two possibilities. It's either going to have n plus 1, a n plus 1 in it, or it isn't, right? There's only two choices here. And notice that they are not overlapping. They're disjoint. So if I were to count these subsets, there's going to be the ones that have a n plus 1 in them, and then the ones that don't have them in them. So the total number will be this sum of those two. And that's how we're going to bring in the addition principle. So we have our first case. Our first case is when a subset contains a n plus 1. Then, what can you say if a subset of size k has a n plus 1 in it? Well, we fixed a n plus 1 in that subset, so that's already been determined. how many other elements can there be in this subset? Well, there's k minus 1 other ones, right? And we have to pick those. So this is going to play a big role in this, and you're going to see it's going to match up quite nicely with something we're seeing up there in Pascal's formula. So watch this. Then k minus 1 elements of this subset are from the set A1, A2, all the way up to AN. So what would these subsets look like? Well, you're just going to imagine every single one of them. You imagine you buy a dozen eggs, but every one of the dozens actually has always a red egg in it. If I asked you how many eggs were not red, well, they're all going to be coming from whatever distribution of the other eggs came from. So we're going to care about those. So if I want to know how many of these subsets exist, it matters what happens with all these k minus 1 other elements, how they get picked. So any subset here can be obtained by including an plus 1. So just imagine you're like tacking this on. It's just like a little post-it note. So you have your subset of size k minus 1 from this set, and then you just tack on an plus 1 like a post-it note. It's like, look, I did all the work of picking these k minus 1 elements. Oh, here's my post-it note. Okay, there's an plus 1. Good job, everybody. That's all we're doing here. Obtained by including an plus 1 with a selection of k minus 1 elements from the set A1 that contains elements A1, A2, A3, all the way up to AN, which has n elements, right? That has n elements. So a question, how many possible subsets are there then? So if all of them are just an plus 1 with that tacked on, it's entirely determined by all of the ones where I pick k minus 1, many of them from n elements. Does that look like something interesting to you? It's right here, right? It's just this. It's right there. Hence, there are n choose k minus 1 many such subsets. Right? That counts for the first case. That means now all we have to do left is we consider all of the subsets that don't contain an plus 1. Because those are the only two possibilities. Either it contains an plus 1 or it doesn't. So let's head over here and let's take a look at the next case. So let's consider when a subset does not contain an plus 1. Well, if it doesn't contain it, then most certainly we're only considering how many elements then of that set? N of them, not all n plus 1 of them, just n of them, right? But we have to choose k of them. So in this case, k elements are from the set A1, A2, all the way up to AN, right? Because it doesn't contain AN plus 1. So how many of those are there? Well, I'll give you a hint. Is that other part of the Pascal's formula. Well, if I have k elements, I'm choosing from a set with n elements. It's n choose what? N choose k. So So there are n choose k possible subsets. Well, now, let's establish the left-hand side of Pascal's formula. Okay, we have n plus 1, gotta be careful here. We have n plus 1 many elements. We choose k of them, right? How many of those are there? How many of them are there? Well, that counts the two cases. Well, the number of subsets of A1, A2, all the way up to AN and AN plus 1, remember there's n plus 1 of them, of size k, by definition, is n plus 1 choose k, right? That's the left-hand side of the formula. But I've considered now how you could get all of these, right? And how many there are. Therefore, by the addition principle, remember, we have the subsets that contain AN plus 1 and the subsets that do not contain AN plus 1. We figured out how many of those there are. That's all the possible subsets, right? All the subsets of size k from the n plus 1 elements. But we determined those counts, and that would be all of those subsets. But we know it's equal to this, and we're done. So we have, therefore, by the addition principle, n plus 1 choose k is equal to n choose k minus 1 plus n choose k. And we're done. That completes the proof. So indeed, Pascal's formula is correct.